Hello and welcome back, folks. Can everybody hear me okay up the back? Yeah, okay, yep, yeah, sadly, yes, they said. We're going to run two 30-minute breakouts here before lunch. And the first breakout session here is Dr. Rotimi Alabi, who's founder and chief executive officer at RAB-Microfluidics. And what he wants to talk about, basically, is improving machine reliability, essentially using automation. But it's beyond me. I will leave it up to Rotimi to explain to you. After you.
Thank you very much, Mark.
You are allowed to clap, by the way.
During my PhD at the University of Aberdeen from 2011 to 2015, I was almost always in the geochemistry laboratories, working on my research in microfluidics. The concept of microfluidics is the manipulation of fluid at the microscale to permit rapid analysis of any fluid sample. What struck me in those years was that all of the samples I worked on commercially did not originate from the laboratories. They came from elsewhere in the world. I worked commercially on samples from North and South America, the Middle East, Africa, Europe, almost every continent of the world. I always wondered how inefficient the process of taking a sample from a particular location and sending it to a laboratory for analysis was, and it concerned the environmentalist in me. Why could we not simply analyze the sample where it originated and give the resulting information instantly to whoever required it? When I completed my PhD, I wanted to focus on this problem. And in trying to focus on this problem, I thought that could I discover what the nature of the problem was? Then I discovered that the problem was even greater than I had imagined. There is a global industry called oil condition monitoring, where lubricating oils are taken from machinery around the world and sent to commercial laboratories for analysis. Millions of lubricating oil samples daily from millions of lubricated heavy machinery around the world. Staggering. But let's take a step back. Why do companies transport millions of samples daily to laboratories for analysis? The answer is information. In the case of lubricated heavy machinery, reliability engineers and asset managers simply want to know the condition of their valuable multi-million-pound equipment, like main engines on a shipping vessel, gearboxes on a wind turbine, pumps and generators on an offshore platform. After my PhD, I thought, if only we could automate the sampling and analysis process, we could generate in real time and on-site the information that reliability engineers and asset managers sought. So I founded RAB-Microfluidics and have dedicated the last 5 years to addressing this problem. RAB-Microfluidics is a technology company that diagnoses early signs of failure in lubricated heavy machinery and prevents such failure from occurring using our patented microfluidic technology. But why does that matter? In March last year, the diesel gearbox on board a shipping vessel of an Aberdeen-based company developed a mechanical failure. This vessel was equipped with the latest condition monitoring technologies, like the vibration sensor, and they carried out quarterly lubricating oil sampling, where they took a sample of oil from the machinery and sent it off to a commercial laboratory for analysis. Despite these measures, the gearbox still developed an undetected mechanical failure that cost the shipping company £250,000 to fix. In December last year, The same problem reoccurred, but this time something was different. This time they had this device on board the shipping vessel. This device told the engineers something was wrong. They investigated and they discovered the problem. This device saved the shipping company £250,000, and it was just a prototype device in pilot trials. This one scenario is commonplace in the maritime industry and many other industries, such as aerospace and defense, processing and manufacturing, power generation, amongst others. In 2020 alone, there were over 1,000 cases of lubrication-related engine failures in the maritime industry. This was 2% of the global shipping fleet. The global market is worth £5.2 billion and growing at a rate of 8.7%. We solved the problem of lubrication-related engine failures by automating the lubricating oil analysis process to permit real-time monitoring of engine condition. We have compacted the entirety of a commercial laboratory into the slim, elegant device. We call it a lab on a chip. This device brings the laboratory to the machinery and allows engineers monitor the health condition of their machines 1,000 times faster and 10 times cheaper than commercial laboratories or existing oil condition monitoring techniques. The technique uses a glass microchip integrated with a UV-Vis light source and a detector to measure and quantify components like acid number, base number, insoluble content, viscosity in microliter volumes of lubricating oils obtained from an operational machinery. The glass microchip consists of a H-cell channel created by wet etching with hydrofluoric acid. The microscale nature of this channel means that low Reynolds numbers operate, so fluid flow is linear and laminar. That is, there is no physical mixing when two fluid streams are flown side by side in the main channel. Consequently, we rely on diffusion across the main channel for the movement of molecules from one fluid phase to another. By varying the residence time and selecting the right solvent, we can selectively extract a component of interest from an oil phase into the solvent extract phase. This component of interest can then be analyzed using optical spectroscopy and quantified using algorithms we have created. Oil analysis data generated by this technique correlates well with laboratory data. Here we compare the results of 3 components: acid number, base number, and insoluble content in lubricating oils provided by several companies. I present the graph of the acid content. On the y-axis, we have the microfluidic technique, and on the x-axis, we have the standard laboratory ASTM method. The data approximates a 1-to-1 gradient fit, where when the acid content in the oil as determined by the standard method is high, the acid content determined by the microfluidic method is also high, and vice versa. There is a similar high correlation for the base number component. Again, when the alkaline reserve in the oil as determined by the standard method is low, the alkaline reserve determined by the microfluidic method is also low. The story is similar for the insoluble content. These data show that the microfluidic technique is correlatable with standard laboratory ASTM methods. We are developing 2 product versions of this technology: a semi-automated portable version that is deployed on-site and used to sample multiple machinery, and a fully automated machine-integrated version deployed on an operational machinery. So how does the technology work? The portable version, which will launch in Q3 this year, analyzes in real time lubricating oils obtained from multiple machinery. Measurement of contamination and degradation indicators, such as acid number, base number, insoluble content, viscosity, metal content, water contamination, typically take 40 to 60 minutes for all analyzable components, and so can be performed routinely every day. Following a measurement, health data is displayed locally on the device and simultaneously transmitted to a cloud analytics platform where modeling is performed, pulling operational information such as running hours, workload, and temperature profile from the machinery. The output is a trendline infograph of the health condition of the machinery in real time and over its period of operation. A simple red, amber, green indicator will inform a reliability engineer when to stop operating the machinery, plan maintenance, or continue normal working operations. The value of this real-time monitoring can be seen in a case study performed on a shipping vessel of a customer. We monitored the two main engines of a marine shipping vessel in over 430 hours of vessel operation. Using one parameter, for example, we can see a continuous gentle rise in the acid content of both engines, but then a sudden spike in the acid content of the port side engine that continues to rise beyond allowable levels. This kind of data is illuminating to reliability engineers and asset managers. Reliability engineers can begin to change the way in which they manage and operate their machinery in real time. For instance, in our case study, a reliability engineer can switch operation to the starboard engine while investigating the port side engine to avoid a catastrophic failure. Also, maintenance can then be planned in advance of this developing fault. We have developed a platform technology that allows us to generate machine condition data that does not currently exist. So, we will use big data analytics to synthesize the continuous large volume of data that will be generated by this hardware technology to forward model machine behavior and create a digital twin, first of component parts and subsequently integrated systems in the machine. The benefits are instantaneous, and they include enhanced production efficiency, better understanding of machine performance, and machine availability. Such automation and digitization can potentially completely revolutionize the oil condition monitoring process and change the way in which machines are operated and maintained. What makes this technology unique and differentiates it from existing solutions is that it can perform in real time and cost effectively too detailed chemical measurements, which until now could only be performed in a commercial laboratory. The technology is the missing link in the suite of automated condition monitoring technologies. It completes the jigsaw puzzle. In summary, we have developed a platform technology that allows us to generate that allows us to analyze lubricating oils in real time. This technique addresses the unmet industrial need for rapid point-of-use multi-parameter testing of lubricant samples. The technique transforms the way in which oil analysis is carried out by automating conventional processes and generating information that can directly feed into predictive analytics models and Internet of Things modules. Our ambition as a company is to develop smarter sensor technologies and have these technologies on every new and existing heavy machinery in the world. This way, we can achieve machine reliability through automation and data-driven solutions. Thank you.
I think, to be honest, you may have missed your call. a teacher, because I understood big chunks of that. I think I understood big chunks of that. Probably I didn't. When you talk about insoluble materials, can I take it you mean microscopic bits of engine?
Yes.
Yeah.
So it could be things like organic solids in the oil and things like soot. So when you burn fuel in an engine, you actually create non-combustible materials, so materials that have not properly combusted, and then they find a way into the oil. And once they find a way into the lubricating oil, they start to build up. And then you have, so when your oil goes into an engine in the first instance, the oil is light brown, it's usually light brown. And then when it's time to service the engine, it becomes black. So what you've seen there as black are all of the particulate material, the soot content that has gone into the oil. And that is what we can track using that technology.
Okay. Any questions for the team? Again, we've got microphones. Just right, one at the back, and I'll come to you.
Hi, yeah, Bruce Cato from North Star Shipping, Group IT Manager there. Loved your presentation. Really valuable in our industry. We have 45 vessels, so condition monitoring is a challenge. What sort of integrations have you done with sort of predictive maintenance, digital twins? Have you had any pilots that you've been doing with any organisations?
That is the next step for us. Thank you for your question, Bruce. That is the next step for us. So what we have been doing following the PhD was try to turn our research into a product that we can actually deploy. So it has taken around 5 years to actually get to that level. So right now we started collecting data that is useful for us to actually do interesting things with. And one of the things we just completed was an Innovate UK project that was sponsored by the Department for Transport on a particular shipping vessel where we were trying to monitor what the information we got from the engine, how it relates with operational data, performance data, and engine emissions. So that was the work that we did. So in terms of that particular work gave us some valuable results that we can then build on. So right now, the next step for us is to actually explore the value add of once you start tracking this data in real time and combining it with performance, operation, and any other metadata you might get from a machinery, what insights can you then get? So it moves beyond just telling an engineer, this is the condition of your machinery right now, but saying this is what is potentially happening based on the way you're operating your machinery. And that is insightful for engineers across board, really, reliability engineers, asset managers, maintenance managers. And the next step for us will be to see what next? What next in terms of can we do digital twins? What does the digital twin look like? Can we start isolating certain parts and understand the elements or the mode of operation of those certain components within the engine? So it is a work in progress for us.
Okay, thank you.
Are you interested in volunteering, Bruce?
I'll definitely have a conversation later, for sure.
I'll take you up on that, Bruce.
Right, the gentleman at the front.
Same question.
Oh, you had the same question? Exactly the same question. Right, okay. How difficult is it, I mean, I don't know whether to ask you this or to bounce it back and forth, how difficult is it to generate a digital twin? If you're talking about a marine engine or something.
I think for me the challenge is that these are all...
Oh, sorry, can I get a microphone? It's good exercise for you, Pete. Crack on.
I'll ask the question anyway, because it kind of builds on that point. And for me, we've got to avoid black boxes. We have the OEM packages on a lot of these machines. We have things like System 1, vibration analysis. We can look at bearing temperatures. We can look at whole bunches of data, but we need to bring it all together holistically. So this looks like a good solution, but it's got to be open. It's got to integrate with those other sources, and we've got to look at the whole picture and then look at the cross correlations.
Absolutely, I completely agree with you. And once you start speaking to engineers and different companies, the first thing is, do we trust it? Can it work? And that is the first point. Does it compare with standard practices? The current de facto right now in the industry is take your sample, send it off to a laboratory. So once you have this kind of technology on board a vessel, for instance, does it give me the same level of data? Then once you have gone beyond that point and where you say, okay, right, we trust the data that is coming from this technology, where does it fit into? How do I then get to use this in a practical sense? So for instance, you have the chief engineer aboard the vessel wants to make real-time decisions based on the condition of the engine. And it has to be able to feed into existing condition monitoring technologies, like vibration analysis that you have mentioned, you have acoustics, you have thermography. You have to be able to see the correlation. And we're currently exploring working or partnerships with a number of providers, service providers, that actually work on the other side of condition monitoring. So they have, they're able to gather vibration data, thermography data, acoustics data, and then the missing link for them is the lubricating oil data. So once we're able to feed into such systems, we then see, right, what is the whole picture of the condition of the engine and how is it being operated? How is it performing based on the way it is being operated? So this is a work in progress, and this is one of the first steps in getting to that point.
Again, this might be a demonstration of my incomplete understanding, but it seemed to me that your device passed what you might describe as the Kalashnikov principle. You know, it's 34 moving parts, drop it in the mud, it still fires. You know, it's passing through that glass chip. It would seem, you know, forgive me if I'm wrong in this, there didn't seem to be much to go wrong there.
Oh.
I was wrong in that. Right, fine, okay, right, okay.
Right, so it has taken us around 5 years to turn what was a PhD research into a commercial product.
Yeah.
Because it went wrong all the time. And that's what it is. We had to be solving technical issues. So currently, we are only able to deploy a portable version. And that is because the portable version was the easier version to actually build and manufacture. What engineers really want is something that actually goes onto the engine where there's complete automation and they don't have to do anything. And the data is fed instantly into existing predictive maintenance platforms. What we have discovered is to actually move from something that is, because in the microchip, you want stable flow. So to actually move from that to an engine that is almost always vibrating, you'll be impacting the microchip. So we have to, that is a technical problem that we have to solve. Now, in the laboratory, you will have ambient temperatures. You can control the temperature in the laboratory. In an engine room, you might have, so we were in Spain the other day visiting a customer, and in the summer, the temperatures got to 47 degrees in the room the engine was, and we have only been operating on 25 degrees. That is a technical challenge you have to solve for a machine-integrated version. So there are a number of things that you actually have to go through to deliver a final product in the case of the machine-integrated version. Most of the challenges we have faced for the technology we have solved for the portable version, and that is why we can now commercially release it next quarter. But it is not a very easy process. The things that can go wrong will go wrong. We have to solve them. And maybe that is why we exist as a company, to solve those problems and ensure that we can deliver to the customer, to the engineer, what it is they actually want, give them the insight that they actually want.
Anytime somebody talks to me about temperature variability, I think about the Apollo spacecraft.
Yeah.
You know, on the sunward side, you were plus 250 degrees. On the dark side, you were minus 250 degrees. You know, it had to be pretty bloody robust. Any other question? That's all. Gentleman there.
Hi, really interesting presentation. Just curious, do you see this being perhaps eventually applicable to other, other, say, modes of transport? Do you think this is something maybe one day could exist inside cars or planes or anything like that to help sort of proactive maintenance?
We do. When we started customer discovery, we spoke to about 300 companies in 6 different industries. And that was really to establish what the problem was and who had the problem and where we could actually address the problem immediately. And one of the companies we spoke to was Magna International. They manufacture engines for a number of the automobile companies. What we discovered in those conversations was that they needed something that was smaller, and they needed something that was hundreds of pounds, because the cars are around, you can get a car nowadays for maybe 10,000 pounds, 15,000 pounds. So in those early days, in as much as that is a potential market, we discovered that the technology was not ready for that kind of challenge yet. So we started shifting into industries that we knew that we could readily address their problems. So the answer is yes, we can solve anything that is any equipment that is lubricated and has lubricating oils that you need to understand the condition, we will be able to measure it. So we have other forms of machinery that you can look at. So you can look at hydraulic oils, for instance, across a number of industries. You can look for transformer oils in the energy industry. So we can look at different types of lubricating oils in different types of industries, depending on the stage of the technology and how readily it can be adapted in that industry.
Okay.
Thank you.
Right. Unless there's anybody else with a desperate desire to ask a question, I'm inclined to round it up there. Rotimi, thank you very much for a fascinating presentation.
Thank you so much for having me.